Half the matter in the universe was missing, but we found it hiding in the cosmos. This is by The Conversation by Javier Prochaska, Professor of Astronomy, Astrophysics, University of California, Santa Cruz, Jean-Pierre Marcat, Associate Professor of Astrophysics, Curtin University. In the late 1990s, cosmologists made a prediction about how much ordinary matter there should be in the universe. About 5%, they estimated, should be regular stuff, with the rest of a mixture of dark matter and dark energy. But when cosmologists counted up everything they could see or measure at the time, they came up short, and they came up short by a lot. The sum of all the ordinary matter that cosmologists measured only added up to about half of the 5% that was supposed to be in the universe. This is known as the missing baryon problem, and for over 20 years, cosmologists like us looked hard for this matter without success. It took the discovery of a new celestial phenomenon and entirely new telescope technology, but earlier this year, our team finally found the missing matter. Origin of the problem? Baryon is a classification of types of particles, sort of an umbrella term, that encompasses protons and neutrons, the building blocks of all the ordinary matter in the universe. Everything on the periodic table and pretty much anything that you think of as stuff is made of baryons, B-A-R-Y-O-N-S. Since the late 1970s, cosmologists have suspected that dark matter, and as of yet unknown type of matter that must exist to explain the gravitational patterns of space, make up most of the matter of the universe, with the rest being baryonic matter, but they didn't know the exact ratios. In 1997, 3 scientists from the University of California, San Diego, used the ratio of heavy hydrogen nuclei, hydrogen with an extra neutron, to normal hydrogen to estimate that baryons should make up about 5% of mass energy budget of the universe. Yet while the ink was still drying on the publication, another trio of cosmologists raised a bright red flag. They reported that a direct measure of baryons in our present universe, determined through a census of stars, galaxies, and the gas within and around them, added up to only half of the predicted 5%. This sparked the missing baryon problem. Providing the law of nature held that matter can be neither created nor destroyed, there was 2 possible explanations. Either the matter didn't exist and the math was wrong, or the matter was out there hiding somewhere else. Unsuccessful search? Astronomers across the globe took up the search, and the first clue came a year later from theoretical cosmologists. Their computer simulations predicted that the majority of the missing matter was hiding in a low-density, multi-degree hot plasma that permeated the whole universe. This was termed the warm-hot intergalactic medium and nicknamed the WHIM, W-H-I-M. The WHIM, if it existed, would solve the missing baryon problem, but at the time there was no way to confirm its existence. In 2001, another piece of evidence in favor of the WHIM emerged. A second team confirmed the initial prediction of baryons making up 5% of the universe by looking at tiny temperature fluctuations in the universe's cosmic microwave background, essentially the leftover radiation from the Big Bang. With 2 separate confirmations of this number, the math had to be right when the WHIM seemed to be the answer. Now cosmologists just had to find this invisible plasma. Over the past 20 years, we and many other teams of cosmologists and astronomers have brought nearly all of the Earth's greatest observatories to the hunt. There were some false alarms and tentative detections of warm, hot gas, but one of our teams eventually linked those to gas around galaxies. If the WHIM existed, it was too faint and diffuse to detect. An unexpected solution in fast radio bursts? In 2007, an entirely unanticipated opportunity appeared. Duncan Lorimer, an astronomer at the University of West Virginia, reported the serendipitous discovery of a cosmological phenomenon known as a fast radio burst, FRB. FRBs are extremely brief, highly energetic pulses of radio emissions. Cosmologists and astronomers still don't know what creates these, but they seem to come from galaxies far, far away. As these bursts of radiation traverse the universe and pass through gases and the theorized WIM, they undergo something called dispersion. The initial mysterious cause of these FRBs lasts for less than a thousandth of a second, and all the wavelengths start out in a tight clump. If someone was lucky enough or unlucky enough to be near the spot where an FRB was produced, all the wavelengths would hit them simultaneously. But when radio waves pass through matter, they are briefly slowed down. The longer the wavelength, the more a radio wave feels the matter. Think of it like wind resistance. A bigger car feels more wind resistance than a smaller car. The wind resistance effect on radio waves is incredibly small, but space is big. By the time the FRB has traveled millions or billions of light years to reach our Earth, dispersion has slowed the longer wavelengths to so much that they arrive nearly a second later than the shorter wavelengths. Therein lay the potential FRBs to weigh the universe's baryons, an opportunity we recognized on the spot. By measuring the spread of different wavelengths within one FRB, we could calculate exactly how much matter, how many baryons the radio waves pass through on their way to Earth. At this point, we were so close, but there was one final piece of information we needed. To precisely measure the baryon density, we needed to know where in the sky the FRB came from. If we knew the source galaxy, we would know how far the radio waves traveled. With that and the amount of dispersion they experienced, perhaps we could calculate how much matter they passed through on the way to Earth. Unfortunately, the telescopes in 2007 were not good enough to pinpoint exactly which galaxy, and therefore how far away an FRB came from. We knew what information would allow us to solve the problem. Now we just had to wait for the technology to develop enough to give us that data. Technical innovation? It was 11 years until we were able to place or localize our first FRB. In August 2018, our collaborative project called CRAFT began using the Australian Square Kilometre Array Pathfinder ASKAP radio telescope in the outback of Western Australia to look for FRBs. This new telescope, which is run by Australia's National Science Agency, CSIRO, can watch huge portions of the sky, about 60 times the size of the full moon, and it can simultaneously detect FRBs and pinpoint where in the sky they came from. ASKAP captured its first FRB 1 month later, and once we knew the precise part of the sky the radio waves came from, we quickly used the Keck telescope in Hawaii to identify which galaxy the FRB came from and how far away that galaxy was. The first FRB we detected came from a galaxy named DSJ 214425.25. It's about 4 billion light years away from our Earth, in case you were wondering. The technology and technique worked. We had measured the dispersion from the FRB and knew where it came from, but we needed to catch a few more of them in order to attain a statistically significant count of the baryons. So we waited and hoped space would send us some more FRBs. By mid-July 2019, we had detected 5 more events, enough to perform the first search for the missing matter. And using the dispersion measures of these 6 FRBs, we were able to make a rough calculation of how much matter the radio waves passed through before reaching Earth. We were overcome by both amazement and reassurance the moment we saw the data fall right on the curve predicted by the 5% estimate. We had detected the missing baryons in full, solving this cosmological riddle and putting to rest 2 decades of searching. The results, however, is only the first step. We were able to estimate the amount of baryons, but with only 6 data points, we can't yet build a comprehensive map of the missing baryons. We have proof the WIM likely exists and have confirmed to identify which galaxy the FRB came from and how far away that galaxy was. The first FRB we detected came from a galaxy named DSJ 214425.25. It's about 4 billion light years away from our Earth, in case you were wondering. The technology and technique worked. We had measured the dispersion from the FRB and knew where it came from, but we needed to catch a few more of them in order to attain a statistically significant count of the baryons, so we waited and hoped space would send us some more FRBs. By mid-July 2019, we had detected 5 more events, enough to perform the first search for the missing matter, and using the dispersion measures of these 6 FRBs, we were able to make a rough calculation of how much matter the radio waves passed through before reaching Earth. We were overcome by both amazement and reassurance the moment we saw the data fall right on the curve predicted by the 5% estimate. We had detected the missing baryons in full, solving this cosmological riddle and putting to rest 2 decades of searching. The results, however, is only the first step. We were able to estimate the amount of baryons, but with only 6 data points, we can't yet build a comprehensive map of the missing baryons. We have proof the WIM likely exists and have confirmed how much there is, but we don't know exactly how it is distributed. It's believed to be part of a vast filamentary network of gas that connects galaxies, termed the cosmic web, but with about 100 fast radio bursts, cosmologists could start building an accurate map of this web. And this is on The Conversation. Stephen Kahn, editor, Creative Commons. Please leave your comments. Thank you for your support. If you'd like to join me on my Patreon account, you will hear content not covered by mainstream media. These riveting stories will be based on my research, and I will state my opinions and give my personal insight on diverse and controversial subjects and world events not covered by mainstream media, and not supported by YouTube guidelines. So whatever I have on my Patreon, most of those will not be on my YouTube channel. Please consider becoming a member today. More of the most significant and important videos will be on my Patreon channel. Your support helps me to continue my research and keeps this YouTube channel alive. And we depend on your support, your generous charity, because we help economically challenged families here in Athens, Greece, in Kapota, and we also help the young generation with university tuition and the community around our church. Thank you.